Okay. Hey guys, today I wanted to talk to you about, okay, I'll just keep going, inference. So chapter 4 starts to introduce kind of the meat and potatoes of this course. Um, we're gonna have to cover a little bit of theory before we kind of get to the fun stuff. So stay tuned. Uh, but also, um, we're going to start with just kind of I hate to belittle it and say with training wheels on, but we are going to start with kind of a very basic version, and then in chapter 5 we're going to move on to what we'll actually be using in real life. So just kind of keep that in mind, that what I'm introducing here, it's just to introduce you to this whole potentially new world of inference. So what is inference? Uh, what is inference? Right? Kind of a weird word if you think about the word. Infer is kind of like you take information from something and you can infer something about a situation or a thing. And that's exactly what we're doing here. And so inference for us covers a kind of a range of things, but it's when we take sample information, thinking like the sample mean, right? To infer something about the population. So when we take sample information to infer something, keeping it nice and vague here, to infer something about the population. Okay. So that's what inference is. Now, it comes in two forms. Okay, so the first one is pretty hefty, and it is hypothesis testing. So you have some theory and maybe about the population mean, right? Is the population mean 4, or is it something else, right? That could be a very kind of basic hypothesis that you have. So a hypothesis is something that you think might be going on, but you need proof, right? And in case this little blurb sounds familiar, that's where we started our kind of, okay, what is statistics? Oh, okay, it's when we take sample information to learn something about the population. And so really statistics at its core is inference. And there are kind of two main pathways that we take. They're definitely interlinked, and I'll show you how as we move through, but interlinked, is that even a word? I said it. So it's a word. Connected, whatever. Hypothesis testing is a big one. Okay. If you're ever reading a study, then they will likely have done some hypothesis testing. The other one, which you'll also see, are confidence intervals. Now, I could talk about confidence intervals and hypothesis testing for way longer than you want me to. But we're going to parking lot it for now and introduce some ideas about, okay, where does hypothesis testing, kind of the basics, come from? And same with confidence intervals. So we're going to build up to it by building up some theory first. Okay, so let me just grab some of this here. Wait. So we will talk about hypothesis testing and confidence intervals for the remainder of the course. So don't worry, you'll get your share. But first I want to talk about the sampling distribution of X bar. Remember, X bar is the sample mean right? That's X bar. So when we're talking about the sampling distribution of X bar, what we're actually saying is, okay, well, where can my X bars come from? Where can my sample means come from? And so up until now, we've really only talked about the distribution of a single observation X. X follows a normal distribution with a mean of 4 and a standard deviation of, I don't know, 2. But of course, in real life, we're not going to be interested in how one individual, whoa, how weird was that one? For some reason, I'm thinking platypus. How weird was that one platypus? If you're sampling platypuses, which is the proper term, because I used to have a test that was platypus themed. They are so creepy. Anyways, I digress. So in real life, we're going to be more concerned with how a mean. So how extreme is it for me to have this sample mean if I'm expecting something else, right? Is there any proof to having a mean of 40 when I'm really expecting a mean of 30? Depends on the spread, right? Depends on the standard deviation. So what we're going to start off and say is that if X, so a single observation, right? So here, this is one observation, X follows a, right, normal distribution with a mean mu and a standard deviation of sigma, then what we'll find is that X bar also follows a normal distribution with the same mean, but the standard deviation of X bar turns into sigma, which is the standard deviation of X over root n. So notice how the standard deviation, and it gets very wordy, right? And I encourage you to maybe write it out, and maybe that's what I'll do here. But first, I want to say that this is a sample mean. Right. And of course, where n is the sample size, but I expect you to be on board with that. Okay. So since the standard deviation of the sample mean, is the standard deviation of X divided by root n, right? That all kind of cut to the chase here. The wording becomes kind of tricky, right? So the standard deviation of the sample mean, right? So the standard deviation of X bar, the sample mean, which is X bar, is the standard deviation of X divided by root n. So notice how we have the standard deviation in there twice, but it means different things. And so instead of having to talk through that every time, what we end up doing is we call sigma over root n, instead of calling it the standard deviation of the sample mean, which is the standard deviation of one observation divided by the root of the sample size. Instead of saying that all the time, we replace it and we call it the standard error. Okay, so we call it the standard error to simplify terminology, despite what it might feel like, right? Maybe it feels like, oh, more terminology. Yeah, and there's more to come, don't worry. But but just, yeah, so if you're still not convinced, then this is going to be a big thing that we're going to come back to, knowing what the standard error is, right? And so knowing that the standard error is sigma over root n, and that the standard error is the standard deviation of the sample mean, okay, which is sigma over root n, that's going to come back a lot. Okay, so I'm going to bring up some more notes here, but give me a little pause here. Okay, so this X bar follows a normal distribution with a mean mu, which is the same as the mean of a single observation, which I do want to talk about, but hopefully it feels a little bit obvious. And a standard deviation of sigma over root n, right, which we'll look at some more. But so notice that the only thing is that now we're talking about the behavior of the sample mean. And so we have to take into account the sample size. And so what's important is that this thing here, so this X bar follows a normal distribution where the mean mu and sigma over root n, that is the sampling distribution of X bar. Okay. And so here, this is the sampling distribution of X bar. Okay, so that is the sampling where we're pulling these means from. And if we think about it for just a little bit, okay, so if all our observations follow a normal distribution, right, centered on some mean with some spread, okay, then it makes sense, or at least I don't think it's that big of a stretch if I tell you that, okay, now if you take sample means, so let's say you've got, let's talk about heights of university students, right? And so, you know, some people are short, some people are really tall, and, you know, most people are kind of, and so heights are something that definitely follow a normal distribution where there's an average height, and it makes sense to talk about the average height. And so heights follow a normal distribution. Now, if I take, I randomly sample 30 students, and then I take their heights and I average them, and then I put them back in, you know, I put them back in my population, and then I randomly sample another 30 students, okay? And then I record their average height, and then I put them back in. Maybe this would have been more fun to think about if I was fishing or something. But anyways, I've committed. So, so now we're collecting this sample of averages, right? Of sample averages. So I've got a sample of sample averages. I know. Whew. Right? And what we're going to find is that we might find that some averages are quite a bit lower than others, and some are quite a bit taller, right? I can't think of a group that's notoriously short, but maybe if we think about, you know, you sample only the basketball team, for example, then your average might be a little bit taller, but as a whole, these averages will still follow a normal distribution. And if the height of all the students is centered on, I don't know, I don't know what the average height is. I really overcommitted to this height example. Anyways, let's say, I have no idea what it is, but let's say it's my height, 5'7". So, although let's do centimeters, 170 centimeters. So let's say the mean is for the population is 170. Then where am I expecting all these sample means to float around, right? All these sample means that I'm collecting and recording, I'm expecting them to be around 170 because that's where my population is centered on, right? So it makes sense that when we go from one observation that's centered on some mean mu, in my case 170, right, in my kind of fake example, I don't want to get in trouble. Anyways, I think we all understand. And so now if to have a collection of sample means, then the shape kind of stays the same. The mean stays steady. What happens is these means are going to be closer together, right? And that's what's reflected in this sigma over root n. Notice that this sigma is the same as this sigma, right? So this sigma came from the spread of a single observation, right? What's the spread in our population? Okay. And then depending on my sample size, right? And we're going to talk more about how this n affects the standard error, but depending on my sample size, I'm going to be dividing by root n. And so, spoiler alert, the larger my sample size is, I'm dividing by a larger number, which means ultimately I'm going to end up with a smaller number, right? And so if I'm taking large samples, say 100 students instead of 30, right? So I've increased my sample size. And so now my sample of 100 students should be pretty close to the population mean, right? Unless I have this like really weird, potentially not random sample, right? But we're always assuming that we're randomly sampling so that we get a good sample. But my sample mean, right, should be pretty close to my population mean. And it should be closer than anything that we would expect in just from a single observation, right? And so these averages are going to hover around the population average and they're going to be closer to it. And that's why we have this adjustment for the standard error. Okay, so the variability of X bar depends on the sample size. Okay, variability, we use variable in a lot of different contexts, right? A variable is a column in your data set, right? So it's anything that we've collected information on. Variability is what type of spread or what type of activity are you looking or are you expecting to see in your sample or in your population? And then variation or variance is the measurement of that. So you have to kind of keep all those words on lockdown. So we expect to see more variability, so more spread in sample means from small sample sizes, right? So if you're taking samples of 4 students and you're calculating their average height, then you're not really expecting that sample mean to be as close to our hypothetical 170 as if you were taking samples of size 30 or 100, right? So as you increase your sample size, you can be more confident in your sample mean getting closer and closer to that population mean, right? And I think intuitively that makes sense. Just from the side note area, right? Sigma over root n is the standard error. I often abbreviate it as SE, and that's pretty common. So you might see SE, and that's the standard error. The standard error is what? It's the standard deviation of the sample means, right? So as n increases, sigma over root n decreases. So let's just think about that, right? Sigma over root n. If I'm increasing n, then the root of n also increases. Okay. But then I'm dividing by a larger number, right? So dividing sigma by a larger number. By a larger number. So overall, sigma over root n decreases. Let me just squeeze that in here. So that's good. And that is one of the many reasons that we want to have large sample sizes. That's probably something that you have brought into this course, is kind of the understanding that, okay, well, I know I have to have large sample sizes. Small sample sizes are bad. They're not bad. What makes them bad? Right now, we can kind of talk about what makes a small sample bad. Well, it's because if you have a small sample size, then you have a lot more spread and a lot more variability, and thus your sample mean that you've collected is not as stable or reliable, right? And so that's why it's bad. Okay. Let's do a little example just to solidify some things. So the entrance exam for business schools, the GMAT, given to 100 students, had a mean of 520 and a standard deviation of 120. What is the sampling distribution of the mean, X bar? Okay. So this X bar is not here to confuse you. In fact, it's there to help you because I want you to see the sampling distribution of the mean. It could have just been question mark there, but then I usually put in the X bar afterwards to kind of nudge you along, right? Oh, X bar sampling distribution. Okay, X bar follows a normal distribution. I almost went off to the races there. Okay, let's see here. So let's answer this. Or I almost forgot what we usually do. Let's read through the questions, and then I'll give you a moment to pause it and work through it on your own. So we talked about what is the sampling distribution of the mean, right? And then what's the standard error for the mean of this sample of students? Okay, so now it's asking what's the standard error. As the sample size increases, what happens to the standard error, assuming the standard deviation remains constant? So assuming that sigma is just sigma and it stays steady, then what happens as the sample size increases? Right? We already kind of talked about it, but I'm just making you say it again. And here's the real kind of thinker. If the sample size is doubled, what's the impact on the standard error? Right? So what kind of change in the standard error are you expecting to see? So I'll give you a moment to pause now. Okay, I didn't actually pause it, but we'll come back. All right, so for A, X bar follows from here. Let's take it one step back, right? So 100 students had a mean of 520 and a standard deviation of 120. How about, just to show you, I'm going to write it out. So a single observation follows a normal distribution with a mean mu and a standard deviation sigma. So in this case, X, oops, I almost just went there right away. X follows a normal distribution with a mean of 520 and a standard deviation of 120. Now, usually the wording wouldn't be like this, and I know I'm the only one who's noticing this kind of inconsistency here, but I do want to point it out. So usually it would say something like the scores for the GMAT follow a normal distribution with a mean of 520 and a standard deviation of 120. Consider a sample of 100 students. What's the sampling distribution of the mean X bar? Okay, so that is something I'll kind of adjust potentially, but for now, let's just assume that That's what it says. And that's probably how you would read it anyways. So the mean is 520 and the standard deviation is 120. And so since n is 100, we know that x bar follows a normal distribution also centered on 520. There's no reason to think that from a group where the mean is 520, if I take a bunch of averages, that the average of those would be anything but 520, right? And so hopefully you're sold on that by now, but, and maybe since it's our first one, I'll do x bar follows a normal distribution with a mean mu and a standard deviation sigma over root n. So x bar in this case follows a normal distribution with a mean of 520 and a standard deviation of 120 over the root of 100. Usually I'm lazy, so I just leave it like this. You can simplify it, especially because we're going to be using it in calculations in a little bit. So you can simplify it if you want, or if you want to, you can just leave it like that. It's totally fine. So this is the sampling distribution of x bar. Okay. What is the standard error for the mean of the sample of students? So now the standard error is sigma over root n, which in this case we said was 120 over the root of 100. How about now I'll simplify it a little bit. So I'll just use my calculator here on the side. 120 divided by the root of 100, phew, 12. 120 divided by 10 should be 12, but I don't really trust my own math ever. So, good. As the sample size increases, what happens to the standard error, assuming the standard deviation remains constant? Okay, so for C, I'm going to cheat because we already kind of talked about it here. Or maybe not. I'll say C above, but as n increases, root n also increases. So sigma over root n decreases. Okay. Here's the doozy. If the sample size is doubled, what's the impact on the standard error? Okay. So what we want to do is we want to say, okay, oops. So part D, sigma over root n versus what? Versus sigma over the root of 2n, right? 2n is if I double my sample size. Okay. You might remember square root laws, right? Or exponent laws, technically. 2n is being multiplied, so it's 2 times n. So I'm allowed to split up this, this square root. So this becomes sigma divided by root 2 times the root of n. But this is the standard error, right? And so this is the standard error. Oops. Salt en français. Unintentional. So what happens? We can replace this chunk with the standard error, and then what we're doing is we're dividing the standard error by root 2. So if we double the sample size, then we decrease the standard error by a factor of root 2. Right? Root 2 is roughly, I did it earlier, 1.41. So SC is divided by roughly 1.41. So there isn't that linear relationship that we're expecting, right? Because we've got that square root. So just keep that in mind. Okay, great. Let me pause it and clean up these notes. Okay, so what's nice and cool about knowing the sampling distribution of X bar, that it follows a normal distribution specifically, and knowing the mean and knowing the standard error. Well, if it follows a normal distribution, remember, then we can calculate z-scores, right? So z used to be, right, we used to have z is x minus mu over sigma, right? But that was when x followed a normal distribution with a mean mu and a standard deviation sigma, right? But now, if we're talking about X bar instead, and notice that these little guys link up, right? So this X goes here, this mu goes here, and this sigma goes here. Okay. How far is that X from your sample or from your population mean, taking into account the spread? So now what we can do is, because it follows a normal distribution, right, and knowing the mean and the standard error, well, now we can translate this z-score to be about the sample mean instead, right? And so I'll use the same colors just to show you where things are going here. But X bar becomes the new thing that you're interested in, right? When we were drawing our normal distribution, right, it's where we draw our line is going to be at X bar now. How far is our sample mean from our population mean, right? And later, this is going to turn into our hypothesized mean, but I'm getting ahead of myself. But it's nice to see that now, right? And so X bar, this is my sample mean. This is the thing I'm interested in. How weird was this thing compared to what I'm expecting to see? And then, of course, I have to take into account the spread, which for the sample mean is sigma over root n. Okay, so we're calculating, we end up with the same thing. And once we have a z, that z behaves the exact same way as the other z's did, right? So it doesn't matter where this z came from. When we have a z, we know what to do with it, right? So that's nice. But how we got it is slightly different now because we're getting it from a sample mean, right? How most of these questions go, you have some sort of kind of carrying capacity, right? And so in this case, we're considering a pallet of 10 boxes. I think on the quiz, there might be like an elevator. There's usually like an elevator question. It has some carrying capacity, but they all behave the same way, right? And so let's have a look at an example and how we use this z-score. Maybe a refresher might be nice. Why do we use z-scores, right? Well, z-scores tell us, you know, taking into account the spread, how extreme is this X bar now, right, from mu. And how do we kind of quantify how extreme it is? Well, we use probabilities. So we're going to use this z-score to find probabilities. Probabilities, right, are areas under the curve, under the normal curve. So suppose the mean weight of boxes shipped by a company is 12 kilos with a standard deviation of 4 kilos. Boxes are shipped in pallets of 10 boxes. And the shipper has a limit of 150 kilos for such shipments. So I want to read through each of these parts and then give you an opportunity to pause it and work through it on your own. Some of these are a little bit tricky, right? Kind of first time working through these, but so give yourself a little bit of a break or cut yourself some slack, I guess, because they can be hard. What is the probability? Well, the probability, remember, is the area under the curve. Okay, so as soon as you see probability, right, we're going to think, okay, that's an area under the curve, or proportion, or percentage, right? So what's the probability that a pallet will exceed the limit of 150 kilos? Now, I've kind of nudged you along here and said, okay, we can reformulate this question to ask, what's the probability that the mean weight exceeds 15 kilos? And that's the trick that you'll use is, okay, so if you have 10 boxes and overall their limit is 150, right, then each box, right, the average weight of each box cannot exceed 15, right? And then next part is, what is the mean weight of the heaviest 10% of boxes? This sounds really familiar to that cereal example, right? Except now we're talking about the mean weight. Okay. What's the mean weight of the heaviest 10% of boxes? And then what mean weights capture the central 90% of boxes? Good. So I'll give you a chance to pause it here, and I will too, actually. So I'll meet you back here. Okay. So what is the probability that a pallet will exceed the limit of 150 kilos? So what we really want to know is basically this, right? I'm going to start out and I'm going to sketch out this curve, right? Because I know that these boxes, the weights of these boxes follow a normal distribution because they're weights. And they follow a normal distribution with a mean of 12 and a standard deviation of 4. Now, this is each individual box, right? But we use that to find the sampling distribution of the mean weight of each box, right? So what we know is that we have a mean of 12, and just somewhere down here, I'm going to jot down that sigma is 4. Okay. Now, what I want to know is the probability that 15, right, that the mean weight, what's the probability that the mean weight exceeds 15 kilos? Now, notice that 12 and 4, so the mean and the standard deviation are for a single observation, but we use those for means as well, right? So they're still follow normal distribution. So what we want is, okay, everything above here, this is where it exceeds 15 kilos, right? Or the mean exceeds 15 kilos. Okay. So that's the probability that we want. And what can we do? Well, I can find probabilities by calculating z's first, right? And in this case, because I'm talking about a mean, it's x bar minus mu over sigma over root n. Now, what was our sample size, right? Well, we're talking about a pallet of 10 boxes. So each individual box follows a normal distribution with a mean of 12 and a standard deviation of 4. But now we're talking about the mean weight if we have 10 boxes. So the sample size is 10. So we have 15 minus 12 divided by sigma, which is 4 over the root of 10. Now I'm just going to go ahead and do that here on the side. We get 3 divided by the 4 over root 10. But first I'm finding 4 over root 10 is not a nice number. So 3 divided by that, just going straight to it. And I'm going to use approximately equal because it's a decimal. I am going to write out all the decimals just so you can make sure that you get the same values that I do. 2.3717082245. But remember, as a rule, our Z table only has 2 decimal places for Z, so we have to round properly to 2 decimal places. So we get roughly 2.37 to 2 decimal places. Okay. So, okay, what does that mean? It means that a mean weight of 15 is 2.37 standard errors away from 12 or above 12, because it's positive. So now we can use that for our Z table to find that probability. And to keep it on the same page here, so you don't have to scroll around so much later, I'm going to go take it up here. So using the Z table, we find the area to the left, right? Because the Z table only gives us the area to the left, right? And we want the area to the right, but that's fine, right? The total area is 1, so we're able to find it. But you should articulate what you're finding as you go. So using the Z table, we find the area to the left of Z equal to 2.37 is what? Now I'm going to go to our tables here, and that's from, I don't know when, 2.37. So 2.3 and then join it up with 7 puts me here at 0.9911. So that's the area to the left, right? Is 0.9911. So the area to the right is 1 minus 0.9911. Notice how I'm showing everything that I'm doing. You don't want to leave something out and leave the reader wondering, hey, where'd you get that value from, right? I'm kind of walking through step by step. And that's your goal too. When you're showing your work on a test, for example, or whenever someone's marking your work, you don't want to have them kind of wondering where stuff came from, right? And so just always take the time to kind of walk through each step. So 1 minus 0.9911 is 0.0089, okay? Which means what? Well, that is the probability that a pallet will exceed the limit of 150 kilos, okay? So therefore, can't remember, I feel like I've introduced the triangle dots as shorthand for therefore. There it is. But if you haven't seen those before, they come in handy a lot. Therefore, the probability that, now I forgot what we were talking about, that the weight of the pallet exceeds the limit is 0.0089. Okay. We can think about, okay, well, is that going to be a problem for us? Not really, right? I wouldn't say that this is a very large probability. It's less than 1%. And so hopefully that's okay, right? Otherwise, we would have to make adjustments, just like we did with the cereal boxes. Oh, what happened there? Finger slipped. Okay. Good. Hey, maybe it was, I meant to do that, I guess. Add a page. Okay, there we go. So B, what is the mean weight of the heaviest 10% of boxes? Okay, so same thing. I want to sketch out the curve and try to kind of figure out what I need to get out of this. So I have this curve, still the normal curve, centered on 12, sigma is still 4. And now what I want is I want to know what the mean weight is of the heaviest 10% of boxes. And so what that means is, okay, well, weights definitely increase as we move along here on the number line, right? And so at some point here, we're going to have an area of 0.1. Okay. What do we have to use in order to get there? Well, we have to use the fact that this area, right? Because the Z table only gives us areas to the left, right? And so that area has to be what, 0.90. And so remember how we went and we looked in the Z table for the Z score closest to 0.9, and then we converted it back to some observation. We're going to do the exact same thing, but with the mean instead and the sample size of 10. So using the Z table, we find the table entry closest to 0.90. Okay. We have to use 0.9 because it's always the area to the left. 0.90, and I'm going to get rid of this because that's from before. I know 0.90 has to be on the positive Z side because it's on the upper end of the mean, right? So I kind of cruise along here searching for something that looks kind of close, and I land between 0.8997 and 0.9015. Now here I said just take the one that's closest. And so the one that's below 0.9, you might have to use your calculator, right? But 0.9 minus 0.8997 is 0.0003. And so whereas 0.9015 is, I think of it as 15 away. So this one is 3 away and this one's 15 away. So this one is the closest one. So 0.8997 is 0.8997, which corresponds to, right? So now it's kind of, so this is why I call it working backwards, right? It's because we're starting at some table entry and we're tracing back to a Z score and unraveling it to some X bar, which used to be X in before, but so it's only that minor change. So which corresponds to Z equal to what? Let's see here. Where's my table? Okay. 0.8997 is 1.28. Okay. Kind of working my way backwards here. And maybe what I'll do is I'll bring this in here just to show you so that it's part of the notes. Z equal to 1.28. So then we take Z equals X bar minus mu over sigma over root N. Okay. And now we're trying to find what mean weight is the top heaviest 10% or something like that. And so now I know I have to force Z to be 1.28. So 1.28 is X bar minus, the mean is still 12 over 4 over the root of 10. Now what we have to do is we have to solve for X bar, right? Which means we're going to multiply both sides by 4 over root 10, and then we're going to add 12. So we get X bar is 1.28 times 4 over root 10 plus 12. And I'll do it here because with the root 10, it's not going to make any pit stops here. So 4 divided by root 10, I'll convert that to one number, roughly 1.26, and then multiply that over by 1.28, and then add 12. Okay, so you should get an X bar of, and I'll use approximately equal, 13.61908,616. Okay. So the top, the heaviest 10% of boxes weigh at least 13.62 kilos on average, right? And so therefore, oops, the top, or sorry, the heaviest 10% of boxes weigh at least 13.62 kilos on, and maybe I shouldn't have the S there, it looks weird, on average. Right, and it's on average because it's for the mean. Right? How is the question worded? What is the mean weight of the heaviest 10% of boxes? The mean weight of the heaviest 10% of boxes is at least 13.62, right? But I just wanted to rephrase it in a different way. But if you just wanted to reword the question as an answer, I am very much for that. That's usually what I want you to do, but in this case, I decided to mix it up. So now, what mean weights capture the central 90% of boxes? Spoiler alert, what we're about to do is actually a confidence interval. Okay, and so when we capture the central 90%, 95%, 98%, that type of thing, that's going to be a confidence interval. So later when we talk about confidence intervals, maybe think back to what we were doing here, and you'll kind of piece it together. But so the central, what mean weights capture the central 90% of boxes? Okay, I gotta add a page here. Okay. And this is really silly. I have to turn off my sprinkler. I'll be right back. Okay. I said turn it off, but I actually might move it. Oh well. Not that it matters at all. Okay. So we wanted to find, oh yeah, the mean weights that capture the central 90%. So if we draw it out, oh, maybe I should not make it so cramped here. Whee, lift off. That's okay. So we're centered on 12, sigma is 4. And so sum between two weights here and here will have the central 90%. Now, we've talked about the empirical rule, right? The 68, 95, 99.7 rule, but now we're forcing it to be 0.9 or 90%, right? So that's not one of our go-tos, but that's okay. We can always use the Z table, and I'll show you an easier way in just a moment. Okay. So maybe so we can talk about these. Let's call this X bar lower and this X bar U for upper, right? Because they're both X bars, they're going to be two sample means that capture the central 90% of sample means, right? And so what we want to do is we want to force this area in the middle to be 90%. And we kind of know what we're doing here now, right? So, okay, so if we have 90 here and it's the central 90%, then we have 10% left over, or 0.1, which has to be split evenly amongst the tails. And so here we have 0.05 and here we have 0.05, right? These areas have to be 0.05. Great. Okay, so, all right, let's see here. So what do we do? Well, it's the same type of question that we just solved, right? So if we just take it one step at a time and we solve, you could start with this X bar upper. I'll show you, there's a couple of reasons why I would start with the lower, and most of it has to do with symmetry. So let's start with the lower and go from there. So using the Z table, we find the table entry, right, is all those numbers in the body of the table. The table entry closest to 0.05 is, let's go there and see, 0.05 is definitely on the lower end, right, on the negative Z score side. And so let's see here. 0.05, some really common mistakes that I see are maybe if you went for 0.0049 or 0.0051, we want 0.05, right? Not 0.005. So you want to pay attention to that because they're out there, right? I've even seen people use 0.0005. And I know that sounds silly, but in a test situation, we kind of freak out and there it is. Okay, great. I'm moving on. I know what to do from here, right? So you just want to kind of relax a little bit and cool it. And I think we've seen this before where we're choosing between two values, right? Because both of these are 5 away, right? And so what we can do is we can kind of go in the middle of them if we want to. You can pick one. It doesn't truly matter that much. Okay, but let's see here. So this, either way, we're going to end up at negative 1.6.045 if you want to, right? If you want to be kind of sneaky about it, or picking negative 1.64 or negative 1.65, that's totally fine. For now, right, I'm going to use, let's expand our mind a little bit. What if I wanted to go a little bit more than 90%, right? So one of these is going to be closer and not quite 90%, and one's going to be a little bit more. Which one is it? Okay. So Z, right, is going towards 0 here. And if I'm moving this line, right, closer and closer then my z-score gets closer to 0, right? Closer to the middle. So if I want the 90% to be 90% or more, right, slightly over, then I would have to bump my z out, right, in the negative direction. So then I would use negative 1.65. That is not something that I expect you to do, but it is helpful when we're trying to think about z-scores, right? And so I'm going to use negative 1.65, okay? But we could use either one. So I want to bring this in and just keep it there for a bit. Is either 0.0505 or 0.0495. Okay, here's what's important. You just need to tell me which one you're using, and then that will be fine. Right? And so it doesn't matter. You just need to tell me that, hey, I'm choosing between these two and they're actually equidistant. So here's the one I'm using. Right? So I will use 0.0505, okay, which corresponds to z equal to negative 1.65. Okay, for that lower bound. So if we think about our Z distribution, it's centered on 0. And if we have this kind of symmetry here, right? Negative 1.65, and I want this to be 0.90, and I still want this to be, now I'm forcing this to be, hey, wait a second. I did it backwards. This is why you write out what you're doing. It's either 0.0505 or 0.0495. I will use 0.0505, but then I said a different z-score. I'm going to change this to be what I actually meant it to be, because I did 0.0495. Man, oh man, good thing I caught that. Otherwise, you'd have to rewatch this video for a long time until you convinced yourself that I made a mistake. I do make mistakes. And typically in class, the chat would be blowing up. Hey, you meant to do this. I know. Now there's no one here to police me. So, right, what I'm saying here is that this area is 0.0495. Yeah. So normal distribution is symmetric, right? Symmetric around the mean. And so if I'm going to want the central 90% or slightly more, right? But that's okay. Then what I'm going to do is I'm going to force this to be 0.0495 as well. By symmetry, right? Because the normal distribution, I can kind of collapse it on itself, and because it's centered on 0. So that's the key. Because it's centered on 0, that negative 1.65, it flips over and it becomes positive 1.65 on the upper end. So here, so this becomes 1.65 by symmetry. Okay, so from here. Okay. All right. So that's a lot of work, right? And I'm just going to show you just quickly what we're going to be doing in the future. But what I want you to remember is that you can always do it this long way, right? Where you're finding, okay, I want 90% in the middle, and that would be for a 90% confidence interval. I know that means nothing to you right now, but it will. Okay, so for a 90% confidence interval, you want the central 90%, 95%, 98%, 97%, whatever. We're not going to do all this work that we just did. Although if you do it enough, you'll get pretty quick at it. Instead, what you're going to do is you're going to use the third table that you have. So I just want to take you there and show you. Okay. So this, I consider the negative Z score is kind of the first table, or first page, I should say. And then the positive Z scores is the second page. And then the third page, I called it the third table. But the third page is the T table. Again, means nothing to you. That's okay. Just ignore it. But notice how it has these confidence levels up at the top. Okay. So what, and hey, this looks familiar, right? This is what we just did, sort of, okay? And so for a 90% confidence interval, okay, which is what we're doing, down towards the very bottom, you're going to find a Z star row, right? Fancy. So the Z star row is that Z, those cutoffs that that we had. So I'm going to just copy these in here so that we can just show, or I can just show you what we'll be using in the future. Make sure they line up, otherwise, what a mess, right? Okay. Just to show that I did, you know, kind of mix and match these together here. Okay. So I condensed it so it wouldn't take up the whole page. But what we're going to be looking at is these values here, and then the Z stars here for now. Okay. And notice in our case, okay, we found that we have a Z of plus and minus, right, because of symmetry, 1.65. What we sort of landed on was, well, it should probably be somewhere in the middle. And that's exactly what we see here. And so for the 90%, whoa, I was still in a kind of a thick pen there. It's all right, fun to see. Right, so for 90%, this is the central 90%, is going to be between a Z score of negative 1.645 and positive 1.645. So in the future, this is what we'll be doing. So we will be building confidence intervals, but we'll just have these values and just ignore everything else in the table for now until chapter 5. Chapter 5. So here, right, your Z star, those are going to be your cutoffs. Okay, so in the future, we will use the T table, which is just this one, to find the Z score or Z star cutoff values. Oops. But I'm going to clean that up. Good. And can't tell if I have, where's my page break here? Okay, we're safe. All right. So just as a heads up, right? You're not going to have to do all that work every time. All right, back to business. So I've already said, confusingly, because I did it wrong, but I'm going to use 0.0495, which adjusts this, right, slightly, but that's okay, right? 0.0495, 0.0495. Let me see here, 0.0495 times 2, and then 1 minus that puts me at 0.901. Right. I've bumped it out by 1%, but I'm okay with that, right? Because the way that we found these Z-scores was a little bit fidgety, right? Later, we'll have them just ready to go. But for now, I am using the negative 1.65 and positive 1.65. Okay, so we can now solve for X bar lower and X bar upper. Okay. I'm going to do them kind of side by side here, trying to keep it on the same page. So here we go. Z lower is X bar lower minus mu over sigma over root n. Okay. So negative 1.6, I think 1.65, yeah, is X bar lower minus 12, yeah, over 4 over the root of 10. So I get 4 over the root of 10 times negative 1.65 plus 12 is roughly, so X bar lower is roughly 9.91 to 896,744. Okay. Maybe, just maybe, I'll be able to squeeze it all in if I bump it all over. So then Z for the upper is X bar for the upper minus mu over sigma over root n, which is positive 1.65 times X bar upper minus 12 over 4 over root 10. So again, 4 divided by the root of 10. And I'm just showing you the full numbers just so you can confirm your calculations. Otherwise, you're free to round to 2 or 3 decimal places. Okay. 4 over root 10, okay, times 1.65 plus 12 puts me at an X bar upper of roughly 14.08710326. Therefore, the central 90% of mean weights is between 9.91 kilos and 14.09 kilos. Awesome. Let me clean this up. Okay. So we just talked about the sampling distribution of the mean. And what we started with was we said, okay, well, how about everything that we're talking about follows a normal distribution? Then, of course, if we take means from that distribution, then those means will also follow a normal distribution. That seems reasonable enough. But one really, really cool / mind-boggling thing is that it actually doesn't matter what distribution you're pulling from. And I'll show you where we're pulling from a very skewed distribution, but those means end up following a normal distribution. And that is the central limit theorem. And it is important. It sounds important. It is important. And what I have a little note here that it is section 4.4 in the textbook. So if you're trying to follow along in the textbook, I bumped it up to be closer to what we just covered, because I think it kind of flows a little bit nicer that way. And so the central limit theorem states that the sampling distribution of the mean of any independent random variable will be normal or nearly normal if the sample size is large enough, right? And so here, this is really important. So of any independent or any, should have highlighted just the mean of any will be nearly normal or normal, which means that, okay, well, the more closely that we need it to be a normal distribution, so depending on how important it is that things follow a normal distribution, you would need a large sample size because it depends on the sample size being large enough. Right, and so really what this is saying is that the distribution of the mean will be normal / approximately normal regardless of the shape of the distribution of the population. And again, I'm just kind of squeezing that in here. I should have given myself more room, but that's okay, because we'll talk about it here in a little bit. But if the sample size is large enough, okay, that's really hard, especially in the beginning. Large enough, what is large enough? So how large is large enough, right? And so the answer is it depends. I know that's not helpful either, right? So hey, I've been in your shoes. So what we say is that, okay, well, how important is it that you have a normal distribution? If it's really important, then you have to have a very large sample for you to be confident that it follows a normal distribution. Or the alternative is that the more closely the original population resembles a normal distribution. So if you're pulling from a normal distribution like we saw, you end up with a normal distribution. That's safe, right? Even if you have a slight skew, right, then maybe bump up your sample size a little bit to account for that. But if you're close to if you're pulling from what is close to a normal distribution, then the means will start to follow a normal distribution quite quickly. So in practice, though, some statisticians say a sample size of 30 is large enough. And so when the population distribution is roughly bell-shaped. So if you've got this approximate normal distribution, a sample size of 30 should be safe. Others recommend a sample size of at least 40. This is typically kind of fields dependent. So depending on what field you head into, right? Some say 30, some say 40. It depends on what you're studying too, right? So if the original population is distinctly not normal, so badly skewed, has multiple peaks, or it has outliers, then researchers like the sample size to be even larger. And in that case, kind of the bigger the better. Then you're dealing with kind of cost constraints, right? So then you might be limited on that end. But in terms of how big of a sample size are you hoping for, then the bigger the better, right? And so in our case, right, for us, we will use n greater than or equal to 30, right? Just as a use just as a guideline. I wanted to kind of illustrate, so I did a little kind of simulation, I guess, and what I did was I created this population. So I just generated a sample size of 1,000, and I want you to think of that as our entire population. So now you can see, okay, the distribution of whatever we're looking at is skewed, right? 1,000 data points, and our distribution starts to look like this. And so you can see it's starting to smooth out, and it's looking quite skewed. Skewed in which direction? Skewed to the left, right? Because it's skewed in the direction of the tail always, right? We're interested in these extreme values, so that's why we say it's skewed to the left. And so what I've done is that, okay, we're talking about the distribution of the mean. So a mean of some sample size pulled from this population. Okay, so we're pulling from a skewed distribution, and we want to calculate the mean, and we want to look at the distribution of the means. So what I did was I took a sample of size 1, calculated the mean. It was easy. It was just the thing that I pulled. And so that's presumably, you know, maybe this first point. Okay. And then what I did was I put that one observation back into the population, and then I collected a random sample of size 2, and I found the average of a sample size of 2, and I recorded it, and presume it looks like it kind of jumped down, right? And then I put those 2 back into the population, and then I took a random sample of size 3, and so on and so forth. And so you can see how for these small sample sizes, right, because we're pulling from a very skewed distribution, it's not until about a sample size of 200 where things are starting to stabilize, right? But you can see that definitely once you hit a sample size of, let's say, 500, then these sample means, they are basically the same. You know, you put a sample size of 500 in, you calculate the mean, and it ended up being somewhere here, and then you put them back in, do it over and over again, and then let's check in at 600. We get basically the same number. So things start to stabilize, and this is what it looks like. So from this skewed distribution, right, very skewed distribution, population distribution, right, we see this volatility, right? We see a lot of activity for smaller sample sizes. And because it's so skewed, we need kind of larger sample sizes. I'd say around here at 200-ish, it starts to kind of hover around the same value. Notice the scale here, 0.7 and 0.75. So it's not actually as wide as it looks. Right? You know, always check the scales. Hey, what's our population between? Population between 0 and 1, it looks like. Looks like I just made proportions, but that's okay. All right, so for us, to help ensure the sampling distribution of X bar is nearly normal and the estimate of the standard error is sufficiently accurate, the sample observations have to be independent. Okay, so random sampling ensures this as best as we can, right? It doesn't ensure it. There could still be some dependency, but if you're random sampling, then you're allowed to assume that your observations are independent, right? So you're not pulling, if we're talking about something sort of genetic like heights, right? You're not pulling siblings and that kind of thing, because those observations would be dependent on each other. Or maybe it would be like kids and their parents, full families. Anyways, if you're random sampling, then you can assume that your observations are independent. We're gonna assume that a sample size larger than 30 is large enough. Okay. And then we're also going to have to make sure that the population distribution is not strongly skewed. And the larger the sample size, as we saw, the more lenient we can be with the sample's skew. Okay, great. I think, all right, let me just be right back. Okay, I've said it once, I'll say it again. Hypothesis testing and confidence intervals, they're the meat and potatoes of statistics. Just overall, there's so many different, or there are so many different types of hypothesis testing questions and confidence intervals questions because it depends on the data that you've collected. We're going to go through some of the core ones and they'll serve you well. So but just remember there are others if you continue your stats journey. So I just want to say that from the central limit theorem, it is a really important theorem. Okay, and so it is a really important concept that, okay, I can pull from a non-normal distribution and the means will still resemble a normal distribution as long as my sample size is large enough. That idea is going to be really important. Okay, but there are no, questions that you are expected to answer from here. So it's just about the concept and theory. However, for hypothesis testing questions, yes, you do have to do some work. There are lots of hypothesis testing questions that we could ask. So whenever we want to prove a theory, or you've probably called it a hypothesis before, right? You have some idea and oh, that makes me, sorry, I gotta go grab this funny, just a second. Okay, I found it. So a hypothesis, right, is some idea that you think you have a pretty good, handle on, but we need to do a hypothesis test just to make sure. And so one of my students before, she sent me this, and so I'll zoom in just in case you can't see. Well, okay. So my 4-year-old asked what happens when you drive over a stick of butter. Okay. I said it'll flatten. He asked how I knew that. And that's how we got here. So what I'm saying is when we have a hypothesis in this house, we test it. I'm also saying my wife is away. I thought that was really funny. But anyway, so hypothesis testing is when you gather evidence, right? And you are able to attach some probability, actually setting up. So now time for me to get boring and nerd out a little bit. Setting up a hypothesis test for this would be quite kind of tricky, but it's cute. So let's just leave it at that. What was I saying? I don't know, moving on. I was distracted by my funny. Anyway, so a hypothesis, and if you want to test it, you have to, but that's what I was saying. You want to attach some probability to what you're saying, right? The probability of this happening is so low that we can go ahead and assume that it probably won't happen. Or on the other end of the spectrum, right, the probability of this happening is so low that it's probable that something else is going on here that we don't really know about, right? So it just happening by chance, that probability is so low. And so that's what we're going to build on, right? And these probabilities are just areas under the curve again. So so if you have developed some new drug or vaccine, not to get too apropos, but if you've developed a new drug and you want to advertise it, you don't just want to say that my drug is better than the other drug, right? Drug A, drug B, whatever. You want to be able to say that my drug is significantly better than the other drug, right? Because that's what's going to kind of boost you over the top. So that significantly better, that significance comes from a result that is statistically significantly different from the other drug. Okay? And so that's what we're working towards, is being able to make a statement like that using data. So we collect data from a sample and then we use it to try to be able to determine if we're able to say that it's something is significantly different from something else. So the thing about hypothesis testing is that, yes, we will go through it a lot. There will be lots of different versions that we're going to work through, but the steps are always the same. And two, it's going to be really confusing now in the beginning, but there's really no other way to do it. And so what I want to do is we'll go through each of these steps. I'll talk about them briefly, and then we're going to go into more detail on each of these steps. And then we're going to do an example together. And so each of these kind of run-throughs will start filling in some gaps. So it will feel confusing in the beginning, but I do find that this is the best way to do it, because if I give you all the information right away, you lose sight of kind of the overall goal of this thing. So remember, we're just trying to have this: is there a significant difference between two things or one thing from a number, that kind of thing. So there are 4 steps that we're going to follow for any hypothesis test. And so that's really nice. Once you have these steps kind of memorized, maybe have them, as a guide, but they'll start to flow. Then you can do any hypothesis test. The steps in between, so the things that you do in each step are going to change depending on the data that you've collected, right? But in general, these steps, they're always the same. So we're going to introduce the idea behind each of these 4 steps first. Okay. So the first thing that you're going to do, and you probably did this, I remember, I think it was like Science 9 or something, where we had to think of a project, and then I don't know how long we had to work on it, but it felt like months. And so, we were collecting data very improperly, but that's okay. It's the spirit of the hypothesis test. And so you have probably stated the null and alternative hypothesis of something before. Now we're going to have a little bit more structure. So we're not just going to say that when I heat up this ice cube, I think it'll melt. And I did it once, and yes, it was confirmed. When I run over a stick of butter, it will flatten. I did it once, and now I'm convinced. That's not really how this is going to go, right? But the idea is the same. So you state the null and alternative hypothesis. So you have to lay out, here's what I think might happen. Step 2, very vague, do the test. And I have it in quotes because it's kind of like that's how I articulate it. Do the test. We're going to calculate a test statistic. So here, this is really calculate a test statistic. But I feel like do the test sounds cooler. So that's what I call it, because it makes me think of do the do. Do the do. Step 3, and remember, these are not supposed to mean anything to you right now. We're just walking through them so that you have them in your back pocket. Step 3, find the p-value. The p-value, spoiler alert, is the probability. So it's the area under the curve, but specifically it's the area in the tail. So it's the probability in the tail. Okay, but more on that. We're going to elaborate on that. So I'm just going to leave it here. But find the p-value is really just going to be the area in the tail. Okay. Step 4 is actually a multi-step thing, but it's draw your conclusion. So state your conclusion. And there are 3 steps in there. So I am kind of simplifying things here. But I like to have 4 steps because then it's a nice crutch for me that I can remember, but also kind of build on. Okay, so now we're going to elaborate on each of these 4 things in the next few subsections here. So let me just grab oh, let me just clean this up. Okay, so the first step, right, was state the null and alternative hypothesis. So we start with a statement of the hypothesis that reflects your research question in terms of the parameter that you're interested in. Now, the parameter that we're talking about for now, that we're going to start with, is going to be the mean, or I should say the population mean, for now. And that's the thing that can change, right? And so depending on what your hypothesis is about, that's going to dictate how you complete the rest of the steps. But the steps themselves don't change. So for now, we're going to start by talking about the mean. And so we'll start with inference about the mean for one sample. So our hypothesis will be about mu, right? And so that's what we said here. So how you're going to set these up is, and I've got these little notes down below here. So H subscript 0, you read it as H naught or H null, null 0, H naught. And usually H naught, the null hypothesis. And so this is the null hypothesis. Oops. Okay. There. The null hypothesis is going to be a statement of no change. Okay, so H naught is a statement of no difference or change. So H naught will always have an equal sign in it. Okay, I do that. Sometimes people will do the opposite inequality, including the equal, but I just like to stick with equals and then not equals down here, or you'll see later we have some other options. But for now, right, because it is a statement of no change, so nothing happened. Thinking about the stick of butter flattening, right? What would the null hypothesis be here? Well, the null hypothesis is that it would not flatten, right? The shape of the butter stick would stay the same. There's no change, right? And then what we suspect happens is the alternative hypothesis, typically. Not necessarily, but typically. And so what we suspect happens is that the stick of butter is going to flatten. So, but here, our null hypothesis, that's what we have to assume. We have to go into it assuming that the stick of butter is not going to flatten. And then we'd run over it, and then we're convinced, magically. It's a little bit more harder than that, but the idea, it's the same. So the null hypothesis and the alternative hypothesis have to be about the same thing. In this case, if you're talking about the population mean, they both have to be about mu, right? And so just as a note, mu naught, so I've got this mu naught is just a placeholder for a number. Placeholder for a number from the question. Okay. So that's just a placeholder, and it totally depends on the question. And figuring out this number can be tricky, but H or mu naught is always going to be the number that we want to compare our sample mean to, right? So it's always going to be the number that you're interested in. Thinking about that palette of boxes, right? We had a sample mean of, let's say, 15, I think was that first part, right? And so we wanted to see how extreme that was compared to 12, right? And so mu naught in that case would be 12, right? And then we're trying to see how far is 15 from 12, taking into account the standard error. So, okay, so mu equals, and then some number, 4, 32, I don't know. So H naught is your null hypothesis, and HA or H1, some disciplines use H1 rather, but I use HA, and I tend to use a capital A. Doesn't matter. So HA is, of course, the alternative hypothesis. Now, typically, that's the one that you suspect is true, but you need proof, right? And so it's also going to be a statement of how mu compares to this placeholder, this number from the null hypothesis, right? And so, for example, and it is a really silly example, that stick of butter flattening, but it does illustrate how weird it would be to talk about different things in the null and the alternative hypothesis, right? And so the null hypothesis is that this stick of butter would stay the same even if it was run over, right? But then what if you said, okay, so instead of saying it'll flatten, maybe you'll say something weird like, or if the null hypothesis is that it will not flatten, then the alternative hypothesis can't be it'll turn into a circle, but they're not related, right? So you have to talk about the same thing here in your null and alternative hypothesis. The only thing that differs between the two is actually the sign here in the alternative hypothesis. So we've got a couple of options, but I want you to remember that the sign in the alternative hypothesis is not equal to by default. So it will change depending on the question, right? Do you want to know if the mean is less than 4? Do you want to know if it's more than 4? Right? Do you want to know the probability of exceeding the weight limit of 15, for example, right? Then you want to know if it's more than 15 or significantly more than 12 rather, but we have a proper example coming up. So it's not equal to by default, but some other options are less than, greater than, or not equal to. And I struggle with these less than, greater than, so just, then the alligator never helped me. I'm like, am I the alligator or am I, anyways, but if you make an L and you read it less than, then then it usually works out, right? So less than, greater than, and not equal to. Okay, good. So here, I shouldn't have put it as such a tiny subnote. It's actually quite important and something that people struggle with. So I'm going to blow it up. If you're only concerned with one extreme, so if you have less than or greater than in your alternative hypothesis, we say that we have a one-sided or a one-tailed test. If we want to detect a difference, so you don't really care if it's less than or greater than, you just want to know, okay, is there a difference or not? Then we say we have a two-sided or a two-tailed test. Okay. And so here, these two are one, I tend to say one-sided and two-sided, but if it makes sense to you to think of one-tailed or two-tailed, that's fine. One-sided tests, and this is a two-sided test. Okay. What's confusing is we make note of if we have a one-sided test or a two-sided test in your null and alternative hypotheses, but then we actually don't use it until step 3 when we have to find the p-value. Remember, the p-value is the area in the tail, right? We said the area in the tail, that's the p-value. So now that's when we need to think back, okay, do I want the one tail or do I want two tails, right? And so that's where it's going to come into play. So that's the tricky part about this, and a lot of people struggle with this. So make sure that you've got it kind of under control. So two-sided test. Just highlighting so that when you scroll through, you stop and look. Okay, good. So that's step one. Kind of tricky because we're going to work through an example, of course, but we're just doing our kind of second, in my mind, second pass through of this stuff. So we still have some cracks to fill in, but we're kind of building up to that. Let's see here. So step two is, I call it do the test, do the do, but it's really calculate the test statistic, right? So here, calculate the test statistic. And depending on your null your null hypothesis and your alternative, but it just kind of follows the null hypothesis, depending on the data, which will dictate your null hypothesis and your alternative hypothesis, that's going to tell you what test statistic to find. So far, we haven't called our z-score for the mean a test statistic yet, but it is. Okay. And so far we've only seen one test statistic. That's fine. Okay. But later, I just want you to see that we're going to introduce t-scores, but notice how so very, very similar they are, right? And the only difference here is that here I have sigma and here I have S. And you can do a little compare and contrast here, but you'll see that they're the same, and that's the only difference, right? Sigma versus S, which is your sample standard deviation. Okay. In real life, we're going to use the sample standard deviation because it's unreasonable to think that we know the population standard deviation. That's not typical, right? Because we're trying to learn about the population. So how would we have the population standard deviation? So when I say that this chapter is kind of introducing things with training wheels, this is what I mean, because that's not going to happen in real life. In real life, we're going to be calculating T's, but the basics stay the same, right? So once we've introduced the Z, then we kind of have a good handle on things, and then we can kind of tackle changes that we see for T that come with using S instead of sigma. And then we can just kind of move through it a little bit quicker. Okay, so for now, right, notice these differences, and we'll kind of parking lot that and use Z for a little bit longer. Okay, I think, and add page. Okay, so just a little note here, the z-score tells us how many standard errors, right? Because it's sigma over root n. How many standard errors an observed x bar is from the hypothesized mu naught. So notice that this mu naught is the same as from, so this is from h naught mu equals mu naught. Whee. Right, so that mu naught is mu, right? But our null hypothesis is that mu equals mu naught. Okay. And here I have it. We call the results from this step a test statistic. but I like to emphasize it in the beginning too, right? Calculate the test statistic. Okay, good. So the next thing we're going to do is we're going to find the p-value. Okay, so step 3 is find the p-value. And you know what I want to do? I just want to bring up some more stuff here. Just a sec. Okay, step 3, find the p-value. So the p-value is kind of this mystical creature. And so let's just start with the definition of the p-value. The p-value is, of course, a probability. That's what the p stands for. It's the probability, and just to emphasize that that's where the p came from, the probability of observing something. In our case, we're going to be talking about x bar for now, but whatever your test statistic comes from, right, as extreme or more extreme than what you saw in your sample, right? And so it's the probability of seeing something as extreme or more extreme than what you saw, assuming the null hypothesis is true. Assuming H naught is true. I think I have that down below here, but maybe not. That's okay. It's there now. And I should probably add it to the notes. But anyways, that's... Oh, the dog was down here. Oh, I didn't know. She scared me. In most instances, the p-value will be the area in the tail. Like I said, and I even went ahead and said it at the beginning there, but so most times it's going to be the area in the tail, right? You want the probability of something as extreme or more extreme, right, than what you saw. That probability is the p-value. And so typically it's the area in the tail. It depends on the question though. So and usually if it's kind of switched around, it's to make you stop and think a little bit, or it's an error. But I do have one where it makes you stop and think a little bit, so that's why I'm putting it out there. But otherwise, it's the area and the tail. It's not completely accurate, but I do find that it's really helpful to think of the p-value as the probability that H naught is true. Okay, and so if you rephrase the p-value as the probability that H naught is true, right, and then if we link it back to that kind of obvious example where okay, you've got a stick of butter, and if you run over it, what's going to happen? Well, we know it's going to flatten. But really what we're saying is, if the null hypothesis is that it won't flatten, right, that it stays the same, what we're actually saying is the probability that it will not flatten is very, 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 very small, right? There's some scenario where maybe it doesn't flatten, right? But in general, it will flatten, right? And so if you have a small p-value, that tells you what to do with the null hypothesis, right? And so, and that's where we're headed. So the p-value, you can think of it, and I find it really helpful to think of it as the probability that the null hypothesis is true, right? So, and like I said, the p-value depends on the sign of the alternative hypothesis. So that's where we need to think about if we have a one-sided or a two-sided test. So a one-sided test, so if the alternative hypothesis is that mu is less than whatever mu naught, okay, then if we want to show less than, then we're going to have some test statistic that's down here on the lower end, right? And the p-value, the one-sided p-value, is going to be this area in the tail. It was hard to program it so it would like show that that was the area in the tail. So this is how I ended up programming it, but hopefully you get the idea. So the one-sided p-value is the area in the tail. Notice, notice that this is less than. And that translates to a test statistic below below 0. Right, a negative test statistic. Sorry, I grabbed a little tomato and now I'm choking on the skin. Okay, I survived. Maybe. I feel like it's wanting to come back. Anyways, you know when like tomato skin, it sticks to the back of your throat, and once tomato skin sticks to like a tooth or something, you're stuck with it. Anyways, back to stats. Because so this less than is reflected in a test statistic that is negative, right? Because it has to be below 0. What does that mean? Well, it means that I have to have some sample mean that's less than the hypothesized mean in order to prove that the sample represents a group that's less than my hypothesized mean. So it's all kind of in there, but that's a lot to unpack, right? But the same thing is going on over here, right? So here, this is greater than, which means that the test statistic, is above 0. Right? And so the one-sided p-value here is the area in the upper tail. So far, so good, right? We know how to find these areas. We've worked on that. We've introduced that, okay, even if we're talking about a mean, we know how to find the Z-score for that. So, okay, great. So we know how to do that. But when we have a two-sided test, right, then we're going to be looking at both tails. The thing is, our sample mean can only happen in one of the tails. So what we do then is we find the one-sided p-value. So let's say our sample mean happens to come out above the hypothesized mean, so above mu naught. So then what we do is we find the one-sided p-value here, and then by symmetry, right, we replicate it on the lower end because it could have just as well happened on the lower end and we would still care because we care about a difference. And so then if I replicate it, then I'm just multiplying by 2 to make it happen on both sides here. And that's what I have here. So for two-sided tests, our sample mean will only appear in one of the tails, right? We're only going to have one sample mean. That's okay. But we'll find the one-sided p-value and multiply by 2. Right? And that's how you're going to find your two-sided p-value. Great. All right. Next stop, conclusion. Let me go see if this will all fit here. Okay. So our conclusion is based off of our p-value. You can see the link, right? So the null hypothesis dictates how we calculate our test statistic in step 2, do the test. And then once we have our test statistic, we use that to find our p-value, right? Once we have calculated our Z, then we can go to the Z table to find the area in the tail, which is our p-value. So now next stop is using this p-value to draw a conclusion, or state the conclusion. So we use our p-value to draw a conclusion about our hypothesis. If the p-value is small enough, and there's that kind of cryptic small enough, again, or kind of similar, but we'll elaborate here. We have enough evidence to reject H naught in favor of HA. Okay? Remember, the p-value, if you think of it as the probability that the null hypothesis is true, if it's small enough, and there will be a guide for what is small enough, okay, but if it's small enough, then you say, okay, well, the null hypothesis, the probability of it happening is really small here, or the probability that it's true is really small. So I'm going to reject it in favor of the alternative hypothesis. And that's where we're going to get that significantly different statement from. To determine if the p-value is small enough, we compare it to the alpha level. So alpha is this little Greek letter, what looks like a fish. Alpha level, you can just write alpha level if you want, but we need to know what the alpha level is. So the alpha level is some threshold, and typically we set up our studies and we determine what we're going to use as an alpha level beforehand, just so we don't kind of start to misinterpret things. The default alpha level is 0.05. Okay, so anything smaller than 0.05 as the default, you would have enough evidence to reject H naught. So to determine if the p-value is small enough, we compare it to the alpha level. And then if the p-value is less than the alpha level, okay, we have enough evidence to reject H naught in favor of HA. Now, what I want you to do, and if you kind of don't like memorizing stuff, that's fine. But if you have to commit one thing to memory, it's this, and thus understanding it, of course. But if the p-value is, so start off by memorize this. Okay. Start off by trying to memorize it. Maybe write it on a bunch of sticky notes, put it around your house, and then when you see it, you force yourself to read it, that kind of thing, because it's going to be so important, and it is a really tricky thing that a lot of people struggle with. So if the p-value is less than the alpha level, we have enough evidence to reject H naught in favor of HA. Okay, and so that's how we set up our alternative hypothesis, and typically we suspect that that's true, but we needed enough evidence to show that, okay, the probability, the p-value, that the null hypothesis is true, right, if we think of it that way, is less than 5% or 0.05. Therefore, I'm rejecting it in favor of what I thought was actually going on. But now you have that less than 5% to kind of give you kind of the muscle, right, for what you're saying. So the default alpha level is 0.05. So if it doesn't say, so if a question does not say what alpha level to use, then use 0.05. Sometimes I'll even say use an alpha level of 0.05, but this is the default. We don't really stray. It depends on what you're testing, right? But you could have 0.01, so that's a little bit more strict, right? You could have 0.1, less strict. It depends on what you're studying and basically how strict you want to be. Okay, so for now, even if it doesn't make sense, I want you to memorize this until it does make sense. Okay, I've got a little thing to help you along here, but let's just talk about it a little bit more. So depending on how the p-value compares to the alpha level, we'll be able to state our conclusions in terms of H naught, right? And so if the p-value is less than the alpha level, okay, we have enough evidence to reject H naught in favor of HA. Notice that this is the same, all right? That's the same as what we just said. Okay? And then I've got kind of the contradictory sentence. I'm trying to think math contradictory, but it doesn't matter. I think it's the grammar, math, I don't know. If the p-value is not less than, right? So all I've changed here is the not less than the alpha level, right? Because the p-value either is less than the alpha level or it's not less than the alpha level. It's a binomial situation. Oh, binary outcome, right? It either is or it isn't. Success, failure. No, we're not going to take it down that road. But the p-value either is less than the alpha level or it is not less than the alpha level. And if it's not less than the alpha level, then you do not have enough evidence to reject H naught. And if you're not rejecting H naught, you can't say in favor of something else because you are not rejecting H naught. So you're not getting rid of it. Okay. So I have this, and it is inappropriate. I'll admit that, but it is really helpful. So that's why I'm keeping it, and hopefully you can kind of, hopefully it's useful to you. Our favorite, Snoop. If the p is low, then the null hypothesis must go. What's so bad about that? Right? But it is really, really helpful. I know it's a stupid thing, but right, but it does kind of help you memorize what? Memorize this. If the p is low, is less than the alpha level, okay? So here, so if the p-value is less than the alpha level, we have enough evidence. We have enough evidence to reject H naught in favor of HA. But so what I have here, just to translate to here, right, really what it's saying is if the P is low, how do I replace we have enough evidence to reject H naught? That just becomes there, right? Rejecting H naught. So, so it is really helpful, and it's really funny to see on a final exam, and it's very, very common that I'll see kind of in the margins. This is for in-person finals, but in the margins, if the p is low, then the null hypothesis must go, and it's all underlined, and so it is helpful, and you will need it. So use it if you want to. Okay. But it'll help you memorize that. Okay. So our conclusion is going to have 3 parts. So it's important that we state our conclusion in terms of H naught, since we've done all our testing assuming the null hypothesis is true. Okay, so we used mu naught in our test statistic because we assumed the null hypothesis was true. So once we know the conclusion in terms of the null hypothesis, okay, so it's important that we state our conclusion in terms of H naught. Okay, so once we know the conclusion in terms of H naught, meaning we can either reject it, we have enough evidence to reject H naught, or we do not have enough evidence to reject H naught. Those are your 2 options, only 2 options. we can reformulate the question as an answer. So our conclusion is always going to have three parts. You start off by saying, how does your p-value compare to the alpha level? Is it less than or is it not less than the alpha level? Then if it's less than the alpha level, then you have enough evidence to reject H naught. If it's not less than the alpha level, then you don't have enough evidence to reject H naught, right? So then you state your conclusion in terms of H naught. Do you have enough evidence to reject it or no? And then what does rejecting H naught, for example, mean in terms of the question, right? So let me just bring up the example here, because I've got an example and we're going to use it to illustrate confidence intervals as well. So I'll reuse the same example because part of the hard part of questions, new questions, is just reading and understanding the content. So I am eliminating that, and that's kind of cheating, but it's our first one, so it's okay. All right, and I'm just now remembering that I think there was is this one with a typo? No, it's another one I'm thinking of. Okay, good. So what I want to do is I want to read it and then let you pause it and try it on your own, and then we'll go through it together. So if we measure the DMS odor threshold, so DMS is, I don't know what, I'm guessing dimethyls, I don't know. DMS odor threshold. So it gives an off odor in wine of individual adults, right? So some of us have kind of stronger noses than others. And so it's the threshold at which we start to smell this off odor. The values follow the normal distribution with a mean of 25 micrograms per liter and a standard deviation of 7 micrograms per liter. So that's the general population. So now we're told, okay, here's the shape, center, and spread of the general population. That's presumably you and I, unless you're some sort of secret sommelier. We'd like to know if wine tasters have a lower odor threshold than the general population. Fair enough. We suspect that they do, but we collect a random sample of odor thresholds for 30 wine tasters so that we can confirm our theory. We find that their mean odor threshold is 21.5. Notice that these wine tasters, they're definitely part of this general population of adults, right? But they're making up potentially the lower end of that normal distribution. And so that's what we want to find out. So is this group do they have a significantly lower odor threshold than the general population? Okay, and so, so we suspect that they do, but we collect a random sample of odor thresholds for 30 wine tasters so that we can confirm our theory. We find that their mean odor threshold is 21.5. So a couple of pointers here. What's your sample size? And what's your sample mean? And on that note, I'll let you try it. So pause it and I'll meet you back here. All right, let's do it. So the first thing you have to do, right, step one, is state your null and alternative hypotheses. And we're talking about the mean, right? And so our hypothesis should be about the mean. In fact, it should be about the population mean. Right, and so in general, we have this setup here where H naught is that, so our null hypothesis is a statement, right? And so that's why it has the colon. I can't remember if I mentioned that. I don't think so. So the hypotheses are statements. So that's why you have these colons here. And you're saying that mu equals mu naught. In this case, mu naught equals 25 because, why? We have our sample mean odor threshold. making X bar 21.5, right? Our N is 30. And 21.5, we want to know if that's significantly less than the population mean of 25, right? And so because I want to know, I want to compare my sample mean to 25, that's where I get this mu naught from. So what we get here is that, so H naught is that mu equals 25. And the alternative hypothesis, right, depends on the question. And in this case, we want to know if wine tasters have a lower odor threshold. So I just want to highlight that. That's where it came from. So have a lower odor threshold. So that's where the less than sign came from. Okay. And my alternative hypothesis then has to reflect that theory or hypothesis, right? That mu is actually less than 25. Has to be about the same number, otherwise it won't make sense. So, so in this case, mu naught is 25 because we want to compare our mean of the wine tasters to the population mean. Okay, good. This is a one-sided test then, right? Because I'm only concerned with one extreme. So here I'll highlight this. This is a one-sided test, right? And like you saw earlier, we don't really need this until step 3, but it's nice to get in the habit of just highlighting to yourself that, oh, okay, I have a one-sided test, because then when you scroll back, you can just kind of remind yourself, oh, okay, one-sided test. Okay, good. Step 2, do the test. What we want to know is basically how extreme a mean of 21.5 is in comparison to a hypothesized mean of 25. And so we need to standardize it, and we're going to use our Z-score. And I've got this fancy notation here, but it's really just saying, okay, calculate a Z-score, which is going to follow a normal distribution centered on 0 with a standard deviation of 1. Now, what we've said before is that, okay, any Z-score beyond 2, we're going to start to consider extreme, right? Or in terms of hypothesis testing, we're going to start to consider it significant. Significant means rejecting H naught. Okay, so there's a lot in there, but so if the mean is 25 for the wine tasters, I'd be really surprised if I saw a Z-score larger than larger than -2, right? Meaning kind of more extreme than -2. Just as a rough guide, we're going to use the alpha level for more precision, but just as a rough guide to get an idea of where this thing is headed. So this will be your first check to see if a result is statistically significant, meaning we can reject the null hypothesis, right? So a significant result means rejecting the null hypothesis. So Z, right, we've got our calculation set up here, and rounding to 2 decimal places, we find a Z of -2.74, which makes me think that, okay, it's unlikely that the wine tasters are just one of us, right? They're probably their own group with a mean that's less than 25, right? So that's what we're doing. I've also got a little thinker here. We're not going to go through it, but what if you found a sample mean of 23, right? So instead of 21.5, you found 23. So now all of a sudden, those wine tasters are closer to us, right? We have a mean of 25, we were told. And so does that affect anything in terms of your Z-score? It would become closer to 0, right? Meaning less significant, right? Less extreme. Okay. So now that I have my Z-score, right, I can find the p-value, or rather in general, what we're going to say once I have my test statistic, I can use a table typically, or software if you have it, to find the p-value. So given z equals negative 2.74, I can use my z table to find the probability of seeing a z as extreme or more extreme, right? That's from the definition of the p-value, the negative 2.74. And that's the probability of seeing a z that's less than 2.74, negative 2.74. Right, and then in general, the p-value will always be the area in the tail. Right? So from our z table, we find the area to the left of negative 2.74, z of negative 2.74 is 0.0031. So I'm not going to go through and do that. I'm going to take my own word for it and say, okay, that is our p-value. So in terms of what we're looking at here, and I'm trying to figure out if I have a page break that I'm dealing with. I don't think so. Game over now, if I do. So 25, and then we found 21.5 here. And then this area is the one-sided p-value, right? The probability of seeing something as extreme or more extreme, right? Extreme meaning into the tails. Okay. And the one-sided p-value became 0.0031. All right. Good. So our p-value, our one-sided p-value is 0.0031. That's really small, right? So now let's state our conclusion. Conclusion part 1. You compare your p-value to your alpha level. Is it less than the alpha level or not? So I always justify it by illustrating that I know what the p-value is by saying, since our p-value, and if you really want to get fancy, since our one-sided p-value is 0.0031, it's definitely less than our assumed alpha level because there's nothing use an alpha level of this. So I'm assuming it's 0.05 because that's the default. So 0.0031 is definitely less than 0.05, which means we have enough evidence to reject H naught in favor of HA. And I do elaborate on it a little bit. Yikes. But what I want to do is I want to break this into chunks. So this is part 1. And then your conclusion in terms of H naught is part 2. And then finally down here, I'll come back to this, but what I have is the conclusion in terms of the question. Part 3. Okay. So those are the 3 parts of a full conclusion. So the conclusion is usually worth quite a few marks, right? So you'll want to keep that in mind. But I do want to come back to this. So in other words, if we think of the p-value as the probability that the null hypothesis is true, the probability that the null hypothesis, which was in our case mu equals 25, is true, is 0.0031. So we say that what we've found is too rare to have happened just by chance and still have the null hypothesis be true. So we reject it in favor of something more likely, and that is the alternative hypothesis. Okay. And then I've got, that means that we can conclude that the wine tasters have a significantly lower odor threshold than the general population. And that is because I've rejected the null hypothesis, and I rejected the null hypothesis because my p-value is less than the alpha level. Now, this is cute, but also really important. You either have enough evidence to reject H naught, or you do not have enough evidence to reject H naught. You cannot accept anything. Why not? Why can't you accept something? Oh, I accept the alternative hypothesis. No, you do not. Why? Because in this case, there's a point, oh, let it just catch up here. There's a 0.0031 probability that you're wrong, right? So you can never accept anything. And remembering the fact about the tails never closing on the normal distribution, on the Z distribution, right? So there's always some probability of something happening, right? No matter how small, there's always a probability that we're wrong. And so we can never accept anything. We either have enough evidence to reject H naught, or we do not have enough evidence to reject H naught. Okay. Good. Nice. All right. That's hypothesis testing. So that's a lot. And we're going to do a lot more of it. But let's introduce confidence intervals now. Confidence intervals, I kind of leave till the end because it's usually not a problem for people. It's kind of fun to do. It's a lot quicker than hypothesis testing. So here we go. Let me just bring this up here. For our confidence intervals. And I also wanted to bring in just so you can have that kind of connection. So confidence intervals, like I said, we already actually did a confidence interval. So we've introduced a lot of this theory already, but we didn't really talk about what it was. So hypothesis testing, which we just did, is we use it to establish whether our sample mean is significantly different from a hypothesized mean, right? And so is there a difference, yes or no, right? And so that's all we can use a hypothesis test for. Whereas a confidence interval, it helps us establish a plausible range of values for the parameter. So it gives us this kind of our best guess, and then a little buffer on there. And then we're going to be, 90, 95, 98% confident that we're capturing the population mean. I need some water. Yeah. Okay. So, sorry, that tickle just won't go away. So hypothesis testing tells us if there is a difference, for example, and a confidence interval gives us an idea of, well, how large is that difference? Okay, we'll get there, but that's a good thing to kind of keep in mind, the difference between the two and how we use them. So a confidence interval, like I said, is going to have your best guess at the parameter that you're interested in. So to calculate a confidence interval for mu, we use X bar, which is your best guess at the population mean, right? And then we do kind of this buffer plus minus, and then we have a Z star, which I have more info on down here. So, and then times sigma over root n. Notice sigma over root n, we know that, and that's the standard error of X bar, right? And so, and then I have a note down here. I'll zoom in, but I'll keep it small. Later, we're going to use this setup, but notice how similar it is. The only difference is the S instead of sigma, right? So later, this is the one that we're going to use mostly. Okay. So just kind of breaking down the components here that we've introduced. X bar is the sample mean, which is our best guess at what the population mean might be, right? We're trying to figure out what is the population mean. We're not going to be able to find it unless we collect the entire population and actually calculate it, which we're not going to do, right? And so that's why we have these tools. Z star is one thing, and it's called the critical value, and it's found in the t-table, and I actually already showed you how to find it, right? So we'll do a little refresher when we do our example, but we've already gone through that, so that's good. And good thing you don't have to do it, by hand like we started out doing. Ugh. Z star is the only thing that determines the confidence level of your confidence interval. So like I said, we're going to be building, 90% confidence intervals, 95% confidence intervals, 98% confidence intervals, and that's going to come from this Z star. Okay. Everything else, it doesn't care about the confidence interval or the confidence level, I guess. Sigma over root n is the standard error of x bar, right? And so here, standard error of x bar kind of has its hat on crooked there, like a cool dude. So then what we call this, I think of it as a buffer. This kind of plus minus chunk is called the margin of error. Okay? And the margin of error is usually called ME or MOE. I prefer ME. But some people use MOE, it doesn't matter. But it's the margin of error. So this whole chunk is the margin of error. Okay. I've got the steps laid out here. So to find Z star for a confidence interval, we use the t-table. First, find the confidence level you want in the top row, then find that column or follow that column down to the bottom Z star row to find your Z star. We've got an example, so I'll show you how to, I'll refresh your memories with the example. Okay. Oh, look at us go. This is not the example I had in mind, but I guess I didn't need to tell you that. What is the Z star of a 90% confidence interval? And then we want 95 and a 95, or a 95 and 95, 95 and 99% confidence interval. Oh, CI is a confidence interval. I should put that up at the top here because I use that a lot. And hypothesis testing, I usually write HT. Right, so CI and HT, they're just abbreviations. So we want to find the Z star for a 90, 95, and 99% confidence interval. So here we go. I'm already on the right table. We'll start with a 90% confidence interval and we follow it down to the very bottom here. And we find that Z star is 1.645. 95% confidence interval is the next one we want to find. And if we follow it down, we find 1.960. Moving along, we've got a couple of different options, and I'll only ever ask you for confidence intervals that are on here, right? I'm not going to ask you for sometimes the random confidence interval that I come up with is 97%. I wouldn't do that because it's not on the table, but I don't know, it just comes up. Anyways, so I think it was 99 we wanted. 99%, 2.576. Okay. So here we go. So Z star is 1.645 for a 90% confidence interval. For a 95% confidence interval, Z star is 1.960. And for a 99% confidence interval, I think it was 2.576. 2.576, but I'll confirm that. Let me just check. 576. Good. Back in my day, we had to memorize these. It's not that bad, but it's nice to have the table. Right, so thinking back, because the confidence interval is going to be capturing the central 90%, 95%, 99%. So we can kind of use the 68, 95, 99.7 rule as a crutch. So then we would expect the Z star for a 95% confidence interval to be 2, right? 1 standard deviation, 2 standard deviations, 3 standard deviations, right? So we would expect it to be 2. But we find that it's actually 1.96, which if you take a step back, 1.96 is really close to 2, right? And so that's why the 68, 95, 99.7 rule is just an approximation, but it works, right? So, but if you want it more precise, it's 1.96. And in terms of calculating our confidence intervals, I want you to use 1.96. Okay? I want you to use these Z stars. You're going to be calculating your interval. So you're going to have a lower estimate and an upper estimate, or kind of lower bounds, upper bounds. So when you write out your interval, you have to use proper notation, which includes you're going to use round brackets, and you're going to have your lower comma, your upper. Okay? And so, and it's important that you don't switch these up, right? There is no interval that goes from 4 to 2, right? Because you're always moving up in the number line. So you want to be careful how you write your interval. As a default, so we like to have these default settings, and then we can adjust. As a default, we use a 95% confidence interval. Because it's a nice trade-off between confidence. 95% confident is really good, right? In most scenarios. But we also want precision, right? So if we think about that trade-off for a second, so confidence, the wider the bounds are, the more confident we are. Okay? Whereas precision, so now if we have tight bounds, we have a precise estimate. So think of it like this. If I ask you, how long is this pen? Now, this is a simplified example, of course, but just to give you the idea of a confidence interval. How long is this pen? It's, I don't know, an Apple Pencil. I start off with my best guess. Well, now I actually have to take a step back and look. 20 centimeters feels a little bit long, but thinking about a ruler. Anyways, let's go 15 centimeters. Okay. But then I want to put a buffer on there, right? So 15 centimeters is my best guess. So that would take the place of my X bar here. That's my best guess. So 15, and then I want to put a buffer on there, plus minus. Now I'm really not sure. My eyeballing skills are low. So 15 plus minus 2 centimeters. And then you ask me, how confident are you? Well, with plus minus 2 centimeters, I'm about 70% confident. If I did 15 plus minus, let's do something absurd, 10 centimeters, right? How confident are you? Well, now all of a sudden I'm very confident. I'm 99% confident. There's a chance that I'm off, but I'm 99% confident that I've captured the actual length of this pen in those bounds, right? And so that buffer that we put on, right, the 2 centimeters, plus minus 2 centimeters, or plus minus 10 centimeters, that's the margin of error, right? And so that's this plus minus chunk that we're building here. And so the wider the bounds are, right? So when I said plus minus 10 centimeters, then I've got these really wide bounds. But I was able to be more confident, right? I was able to be 99% confident. Whereas precision, when I was able to say 15 centimeters plus minus 2 centimeters, then I've got fairly tight bounds, and then I'm really, kind of doubling down on my estimate. Then I have a really precise estimate, right? But it might affect the confidence that I have in my estimate, right? So we need a trade-off for that. And I had someone way back ask me a really good question that I think about sometimes is, why don't we make 100% confidence intervals? In order to make 100% confidence intervals, thinking back to Z, right? Because Z star is just a Z. Remember, Z star is the only thing that tells you how confident you are, right? So if we had to make 100% confidence interval, Z would have to be at negative infinity and positive infinity, right? So Z star would have to be infinity, which is not very helpful at all. But that's just kind of a nice link between how Z behaves and how Z star works for your confidence interval. Anyways, I would have to say something weird like, this pen is 15 centimeters plus minus 2 kilometers. I'm 100% confident, right? It doesn't work like that. Okay, good. Where was I down here? Haha. Oh, looks like, all right, gonna clean this up just a sec. Okay. And another thing I wanted to mention, why we use 95% confidence intervals as the default, is also because of its relationship with an alpha level of 0.05 in hypothesis testing. Notice that what happens is, if you consider your normal distribution here, you're either 95% confident that you've captured the center or captured the population mean, or this is 0.025. Remember, the default is a two-sided hypothesis test, right? So that means that 0.05, the alpha level, would be split in two, right? And so 0.025 here, but together they make 0.05, right? And so that's where you're either 95% confident that you've captured it, or you're 5% certain that you have enough evidence to reject the hypothesis. So they are going to work together, and we're going to talk about it but first I want to do a hypothesis or a confidence interval. We've already done a hypothesis. What's really important is we'll always need to interpret a confidence interval. A lot of people forget it. I'll even put on a test, okay, make sure you interpret the interval. It's half the marks. So the calculation is only worth half the marks, and then the interpretation is the other half the marks. Okay. There are a lot of ways that you could interpret it incorrectly. So I want you to, and I'll go ahead and say it, I want you to plagiarize. No, it's not really plagiarism. It's just a statement of fact, right? I want you to use this setup. Okay. So here, once you've found your interval, right? Let's say your interval is from 2 to 4, and it's a 95% confidence interval. We are 95% confident, so it's kind of a fill in the blank situation, that the interval from 2 to 4 captures the population mean odor threshold, or whatever we're talking about. 2 to 4 didn't make sense for the odor threshold, but I think you get the idea. And we'll make one for the odor threshold, so it's okay. We're going to be building confidence intervals for a few different parameters. And so but the concept and the interpretation stays the same, regardless of what we're trying to estimate. So just kind of commit this to memory as a starter. And then later we're going to start talking about something other than the population mean, right? Maybe we'll start talking about the population mean difference or the population difference in means. I know they sound the same, but they're not. And then later we'll start to talk about population proportions, right? But the structure of the interpretation stays the same. So I want to revisit the same example that we did. And of course, I want to let you pause it and work through it on your own. But let's just read through it again. It's the same information. So the population has a mean of 25 and a standard deviation of 7. So we would like to know if wine tasters have a lower odor threshold. We suspect that they do, but we collect a random sample of odor thresholds for 30 wine tasters. So all this stays the same. We find that their mean odor threshold is 21.5. Construct a 95% confidence interval for the mean odor threshold of all wine tasters. So notice before, with the hypothesis testing, we were able to say that, yes, there is a difference. Now we're going to be able to say, okay, well, so what is the odor threshold for these wine tasters? And I don't have it typed out, I realized. So here we go. We'll start with the formula. X bar plus minus Z star. And I guess maybe this is a good time to introduce on the formula sheet, but at this point, you've probably already kind of seen it. Oh, I forgot to bring it in earlier on in the chapter, but here it is. I'm giving you the sampling distribution of X bar and also the Z that goes along with it, but we're about to use it, or we used it in our hypothesis test. So I'm just going to grab this here. So the confidence interval in this case is going to be X bar plus minus Z star times sigma over root n. And that's from here. All right. Sorry, I should have shown you the formula sheet, but I guess now's as good a time as any. I have the default null and alternative hypotheses here. Remember the sign here can change. But other than that, if it's one sample mean that you're hypothesizing about and you know sigma, right? So far this is all that we've seen, so that's why I'm not really emphasizing it. But here's your default null and alternative hypothesis. Here's step 2 of your hypothesis test, right? Do the test. And then the rest kind of follows. But now we're building a confidence interval, and we will be calculating the sample size just briefly at the very end. So just kind of sit tight. Okay, so let's just figure out, right, the components that we have, right? We know that X bar is 21.5. I know that sigma is 7 because it says so in the question. And n is 30. So we need to find Z star for a 95% confidence interval. And in terms of your work, if you just tell me that it's 1.96, that's fine. I'm gonna write out how I found it because it's one of our first times. So using the t-table, oh, I want it back to yellow here. Using the t-table with a confidence level of 95%, we find that Z star is 1.960, or just 1.96 if you want. So I'll show you how I found that. So I'm here in the t-table, table C, the t-distribution, and I find a confidence level of 95%. So 95%, if I scroll down, I follow it down to the bottom, then I find Z star is 1.96. So that's what I'm using. Okay, so now I have everything that I need, all the components to build this confidence interval. You can see how it's quite a bit easier than hypothesis testing. So I'm going to start off with my kind of blank slate here again, and I'm going to fill in these values. Remember, 21.5 is the sample mean odor threshold for the wine tasters. And so now that's my best guess at the population mean odor threshold for wine tasters. Right? So here we go. 21.5 plus minus 1.96 times 7 over root n. Now I'm just going to go ahead. Oh, sorry, not root n, root 30. So what I'm going to do is I'm going to have 7 divided by the square root of 30 and times 1.96. So I find 21.5 plus minus 2.50491783. And just as a heads up, this is the margin of error is 2.505, but let's just do 2.5. Oh, add a page here. Okay. So rounding to 1 decimal place, which I know is really kind of cheap of me, I guess. But it's just because I want easy calculations. So then I get 21.5 plus minus 2.5. We should keep more decimal places, but I'm just being lazy. So 21.5, see how it's plus and minus? You're going to want to start with the minus because otherwise you'll get tripped up when you go to list your interval. Remember, your interval, you have to list it with round brackets around and then separated by a comma. So you want to find your lower bound first. 21.5 minus 2.5 puts me at 19. And 21.5 plus 2.5, so going up now, is 24. So from my sample mean, 21.5, I've gone down a little bit, up a little bit. Now it's time to interpret this interval, right? What does this interval tell me? We use the same structure that I outlined earlier, right? So we are, I like to use the we, just we're a group, we're here together, or the royal we. Might be fun to think about. We are 95% confident the interval from 19 to 24 captures, and it's really important that you have this captures because you're trying, we don't know what the population mean is. We're trying it, but it's fixed. So thinking back to this pen is some exact length, depending on how precise your measurement measuring device is, it does have some exact length. And that would be the same as the population mean. We're just trying to capture what it is, right? And so it's kind of like if you think about putting a cage down, but your eyes are closed, right? Did you catch? So you've got maybe a marble on the table or something, and you're trying to capture it, but we don't really know. We're 95% confident that we did, but who knows? Maybe this was just a weird sample, right? Maybe it's not representative of all wine tasters, right? So that's the glitch. So that's why we use captures. So we're 95% confident the interval from 19 to 24 captures the population mean odor threshold of wine tasters. Right. Sometimes I'll even emphasize it, right? But it's important that we say the population mean. Odor threshold of wine tasters. And sometimes I'll even say something kind of redundant, like of all wine tasters, because saying the population is all wine tasters. But you just want to emphasize that, okay, we're trying to capture the population mean. Okay. Good. So in terms of your interpretation, this would be half of the marks, right? So the calculation is half the marks. That's work, right? But the interpretation is the important part. Okay. So one kind of fun thing is that we can use a confidence interval to test a hypothesis. I'm going to just bring it up here. And I want to like really highlight this. Now that we've introduced both a hypothesis test and a confidence interval, we can use a confidence interval to test a hypothesis. If the hypothesized value falls inside the confidence interval, okay, so thinking about our interval here, 19 to 24, our hypothesized value, thinking back to our hypothesis, our null hypothesis was 24, right? 25. 24 is in the interval. 25 is outside this interval, right? If you're thinking about a number line, 19 to 24, and then 25 is out here, right? Meaning that 19 to 24 did not capture 25, right? And so if the hypothesized value, which in our case would be 25, falls inside the confidence interval, we do not have enough evidence to reject H0. While, and this is what's happening here, if the hypothesized value falls outside the confidence interval, we have enough evidence to reject H0 in favor of HA. So the null hypothesis was that mu equals 25. So what we landed on with the hypothesis test was that, nope, the mean is less than 25, right? The confidence interval tells us that the mean, the population mean, we're 95% confident that the population mean is somewhere between 19 and 24. And so that's the same, it's kind of approaching it from a different angle, right? But it's the same thing as saying that it's less than 25 because this entire interval is below 25. So that's something really cool and really important, and something that I'm going to come back to, right? So I'll make you do a confidence interval and then maybe use it to test a hypothesis, right? That's going to be something that we're going to do. All right. So now that we've introduced confidence intervals, the last thing, hypothesis testing, confidence intervals. Last thing I want to do is just looking at how do we calculate the required sample size. So maybe before you set out and collect data for your study, right, you might want to figure out how big of a sample am I going to need here to be able to say what I want to say, right? And that's pretty common. We're going to do this more with proportions later in chapter 6, but we can do it here as well. Given sigma, which is the population standard deviation, so that's kind of weird, but it's okay, we'll pretend. So given sigma and a desired confidence level, which is going to be reflected in our Z star, and a margin of error, which we're denoting by a lowercase m, we can calculate the sample size n required by using this formula. And so that's what we had on our formula sheet down here, right? So you take your Z star, you multiply it by sigma, and then divide it by m, and then square it all. This is really just rearranging from the confidence interval, right? You've got your margin of error, which you're denoting by m, and then you're solving for n. So as a quick example, if we want to decrease our margin of error to plus or minus 2, notice that before we had a margin of error of 2.5, right? So now let's pretend that we want to decrease it to 2 with a confidence level of 95%. So keeping it at 95%. How many wine tasters will we need to sample? And then I've got a little reminder that sigma is 7. And also keep in mind that since we can't sample a portion of wine tasters, right? So we can't sample half a wine taster. You're going to need to round your answer up to the nearest whole value, regardless of the decimals. So even if you end up at 10.01, you would need to sample 11 wine tasters. So let's just have a look at x bar plus minus z star times sigma over root n for a second here. We said that this is the margin of error, which we're denoting by m. Okay. So we want to know what n is going to decrease this m to be just 2. So we can use it this way, and you can definitely just use this calculation if you want to and rearrange the fact that m equals z star times sigma over root n and solve for n. Or n is, so that's, it's just been solved for you, right? Z star times sigma over m, and then square it. So I'm finding n is 1.96 because it's still for a 95% confidence interval times 7 divided by, now I want it to be 2 squared. 1.96 times 7 divided by 2 and then square it, I get 47 point, I just feel like I messed that up. Let me just check. I did not. Great. So I get an n of 47.0596, which means that therefore we would need to sample 48 wine tasters, right? Because you'd have to round up. I can't sample 0.0596 of a wine taster. I can only get opinions of whole numbers. So people, or I guess odor thresholds. So we would have to sample 48 wine tasters. Okay? This is something that we're going to do in a different scenario more, so that's why I'm being kind of brief here, but it's kind of fun to see. So our margin of error was 2.5. Where is it here? It was 2.5 when we had a sample size of 30, if we bump it up to 48, we can decrease that margin of error to be just 2. All right, so let me just check here, but I'm pretty sure, we have reached the end of the road for chapter 4. So a pretty good, pretty brief, but good introduction of a lot of different information. So hypothesis testing, confidence intervals, we'll build on those, but really good work. All right, see you next time.